Okay, so this afternoon we are going to look at another way of finding the root to nonlinear equations. This time around, we're going to look at something referred to as an open method. Open in the sense that we do not use a bracket to enclose the solution. But all open methods are also referred to as slope methods. So instead of using a bracket to enclose the solution like we did with bisection, what we actually use are slopes. So we are going to, as you are going to see in the diagram which we have here, we make a slope. Then using this slope, we use this slope to estimate what values of x are in terms of the solution. So what we start with, you have to start with a particular value of x. So some guess value of x. In this case, I start with x naught here, x0 here. So I have got x0 here. Then at x0, I draw this dashed line here. This dashed line meets my function f of x at this particular point. So at this value, at this point where it meets, the dashed line meets your f of x, that is the value of the function at x naught. That's what you have here as your x naught here. Then at this particular point, what you do is you draw a tangent, which is this tangent which you have here. So you draw this tangent, you extend this tangent until it crosses the x-axis at x1. Is that clear?
Yes.
Yeah. So you draw a tangent at this particular point until it crosses your x-axis at x1. When it crosses your x-axis at x1, x1 becomes your new solution. Are we clear? So x1 becomes a new solution. Then if x1 becomes a new solution, then you draw another dashed line going up where it until you reach a point where it meets the function f of x. So at this particular point where it meets the function f of x, this becomes your f of x1. Then you draw another tangent at this particular point. When you draw another tangent, it comes like this up to this point where it meets the x-axis. This becomes your new solution x2. Okay, then at this particular point x2, again, you can see that small dashed line there. So you dash your line up until where it meets your function f of x. Then at that particular point f of x, again you draw another tangent, and hopefully this time around your tangent is going to cross the x-axis at a position which is acceptable as a root. So these open methods, like as you can see from here, our guess, we started with the guess value of x1 of x0. Then we drew a tangent at this point where this dashed line meets our function f of x. We drew a tangent. That tangent gives us, when you extend it downwards, it crosses the x-axis here. We get a new value of x1, a new solution, which is x1. We get this solution x1. Again, we draw a tangent like that. Then we get our x2. At x2 there, again, you draw a tangent at x2, which meets the x-axis. Hopefully you get your root. Now, in reality, we do not go about drawing tangents. Are we clear? We do not go about. Basically, this is what we do in form of a picture. But that's not exactly what we do. So what we actually do is we use the definition of a slope or the gradient. So in this case, if you draw a tangent, like we have done here, you have your point x naught, then you have the value of the function at x naught, then you have this other point here, x1, then you know what the value of the function at this particular point is. Okay, so we use this here. We use this as a way of defining the slope. So when you do that, we're going to define our slope, which is also equals to the derivative. So our slope is going to be equals to, which is, we're looking for the slope at this point, at x naught. So we're looking for the slope at x naught. So our slope at x naught with our tangent, which is just the derivative in this case. So the slope of the function f of x at x naught is just the derivative of this particular thing, function. So that's going to be the derivative of the function at x naught is going to be the change in y. So you have got this particular bit here, the value of the function at x naught minus the value of the function at x1. So the change in y, so that's what you have here. So f of x naught minus f of x1. Okay, then divided by the change in x. So the changes in x is going to be this x naught minus x1. So you end up with x naught minus x1. Now, what we are looking for is this x1. We are looking for x1, and if we are looking for x1, we are going to treat x1 as a solution. So if x1 is a solution, then it must satisfy this condition. F of x1 must be equals to 0 if we are going to treat x1 as a solution. Are we clear? If x1 is going to be our solution, if that's what we are saying, say, oh, x1 is a solution. If x1 is going to be our solution, then x1 must satisfy this condition. When we get x1, we put it in our function f of x, it should give us 0. Are we clear? Is it?
Yes, sir, we are.
Yes. So if we are saying, after we do this derivative business here, we use the definition of the derivative. Say the derivative is equals to the change in y, which is f of x0 minus f of x1, then over x0 minus x1. If we are saying that, we are using this method to find the solution x1. If x1 is going to be taken as a solution, then if we put x1 in f of x, it must give us 0. So basically, I don't know whether it's by definition or by implication, if we are saying x1 is our solution, then f of x1 must be 0. Are we clear? Is it clear?
Yes, we're good.
Therefore, this bit f of x1 is going to become 0. So we're only going to remain on top here. We're just going to remain with the derivative of f of x naught is going to be the value of the function at x naught divided by x naught minus x1. Now what we are trying to find is x1. We already, what you're trying to find is x1. So in this case, when you multiply both sides by this bit, we end up with x0 minus x1 multiplied by the derivative at x0 equals to, if you multiply this side by that, you end up with f of x0. Next, if you divide both sides by this derivative, the derivative of the function, the first derivative of the function at x0, if you divide both sides by that, you're going to end up with this side, you're going to remain with this, you're going to remain with, x0 minus x1 equals to f of x0 divided by the derivative of the function at x0. So basically what you're seeing this side is that when you start with a guess value of x0, you need to be able to work out what is the value of this function at x0 And also you should be able to work out the derivative of this function so that you find out what the value of the derivative is at x naught. After that, we are interested in getting this bit, x1. So we get this stuff, this f of x naught divided by f of that, we take it to the other side, then this other thing, we take it to the other side. When we do that, we are going to end up with the following. You're going to end up with no, I made a mistake somewhere. So when this goes to this side, then that goes to that side. So this side we're going to end up with okay, fine. No, I haven't made a mistake. So I get this bit, this part, I take it to the right hand side. When I take it to the right hand side, I end up with x naught is equals to x1 plus f of x naught divided by f of x2. Then I get this rational thing I have here. I take it to the other side. When I do that, I end up with x1 is equals to x naught minus f of x naught divided by the derivative of the function at x naught. So this is how we use the definition of a derivative or a slope to come up with a way of estimating what x is going to be. So with this expression, basically what we are saying here is that if you have a guess value of x naught, you know what a guess value is. You choose whatever guess value you want to start with. Then this guess value, you find out what the function is at x naught. Then you also work out the derivative. Then you find out what the function is, what the value of the derivative is at x naught. When you plug in these numbers here, what you're going to get is you're going to get x1, which is going to be your root. Then after you get your x1, like in this case, if you look at the diagram which you have here, yes, x1 is closer to where the root is than x naught. So your new root becomes x1. Okay? Then you use this x1, you put it back in this expression. So now that you have got x1, you use this x1, you put it back in this expression. In place of where there's x0 here, you put x1. In place where there's x0 here, you put x1. There you put x1, so that you end up with x2. So when I do that here, I end up with x1 minus f of x1 divided by the derivative of f at x1. So when I do this again, this should give me x2, which is the x2 which I have here. Are we clear?
Yes, sir. Yes,
Yes,
good.
yes, sir, we are.
Yes. Then I'll keep on doing this. So with this x2, I'll keep on x2. I put x2 here. Then I find out what the function of x2 is there, and what the function of what the value of the derivative is at x2. Then when I do this, I should get x3. Then I get the x3. I put it back in. When I work it out, I should get x4. Then x4, I put it back. I get x5. So basically, you use this formula. This formula is what is referred to as the Newton-Raphson method for finding the root of a nonlinear equation. So this whole thing which you have here can be rewritten in terms of subscripts k, which is just the number of times you've done something. So you write it for you to find, for this one, x, for you to find based on xk, which is the root, your guess value, and your k's start from 0, 1, 2, 3. So from xk, you get your xk, you find out what the value of the function is at xk, then you also find out what the value of the derivative is at xk, then you put your xk here, the value of the function at xk, the value of the derivative at xk there, you should get your xk plus 1. Then you get your xk plus 1, you repeat the process, you get your next value like that. Are we clear?
Yes.
Yeah. So you are expected to understand what this thing is doing. Of course, We are not interested in you deriving these expressions. Absolutely not interested. Our interest is in you using these expressions to find out what we need you to find. So to start with, we are going to go back to our example. Example number 3, we look at the same function which we looked at. This is a function we looked at with bisection. So find the root of the equation. F of x is equals to x to the power 5 minus 2 x to the power 2 minus 3 equals to 0. So this function we have seen before. This is a function which you have up here. Plot of that function is what you have, I think, up here. If I go up, no, not this one, the first one we looked at with bisection. This one here. So this is our function. F of x is equal to x to the power 5 minus 2 x to the power 2 minus 3. So this is what our function looks like between 0 and 2, somewhere there. So what we are doing ourselves, we are starting with a slope which is going to be made at x naught equals to 2.0 here. So our slope starts from this side. So we make our slope like that, then we keep on making new slopes until we come up to here. So with that, so we at least we know where our x0 is. X0 is 2 here. Now there is no, you can choose whatever value of x is, whatever value of x2 is, and the closer your value of x is to where the root is supposed to be, the better. So in our case here, our root is somewhere at 1.5, somewhere there. So if we choose a value of x naught, our starting value x0 equals to 2, it's close enough. So we can use that. Okay. So let's see. Okay, so we are going to start with our x naught at 2, and this is a function. So the first thing about you need to be aware of about the Newton-Raphson method is that it's necessary for you to be able to work out a derivative for this particular function if you are going to use Newton-Raphson method. Here, f prime is the derivative. So if you have a function and this particular function's derivative is easier to work out, then you can use Newton-Raphson method. But if the derivative is not easy to find, then you should look for something else. Either you can look for bisection, or as you're going to see, there's a method called secant which you can use. Okay, so the first thing which you're supposed to do is you should be able to work out the derivative of the function you've been given. Are we clear?
Yes, we're good.
We use Newton-Raphson method with functions which are easily differentiable. Okay, so we should be able to do this, find the derivative of the function f of x. So in this case, the derivative is going to be equals to f prime x is going to be equals to, that's going to be 5 4 to the power x to the power 4 minus this bit here, that's going to be 4x, then this one is going to be 0. So our derivative f prime of x is just going to be 5 x to the power 4 minus 4x. So this is easy to find. Okay, next, for the first iteration, and as you can see, our iterations, our k's, which is the value for the iteration, for first iteration, our k's start from 0. So for k equals to 0, for the first iteration, which is our k equals to 0, when we replace in this expression here, where there's k, we put 0. So everywhere where there's a k, you put a 0 there. So here, you're going to have 0 plus 1, that's going to give you a 1. Here you're going to have a k, x0. Here you're going to have an x0. Here you're going to have an x0. The Newton-Raphson method becomes x1 is equals to x0 minus f of x0 divided by the derivative of the function at x0. Is it clear? You just put in the value of k in that formula. So it should come out like this. x1 is equals to f of x0 minus f of x0 divided by the derivative of x at x0. Is it clear? Is this bit clear?
Yes, sir.
Okay, now as you can see, we have the value of x0, which is a 2 we've been given here, but it's necessary for us to find out what is the value of the function at x0 and what is the value of the derivative at x0. So in this case, since we know what f of x is, it's just a function. That's the expression we have here. That's what you have here. So you substitute in the value of x0. So we have to evaluate f of x0 and also the value of the function at x0. So f of x0 is going to be equals to f of 2, which is going to be 2 to the power 5 minus 2 times 2 to the power 2 minus 3, and that's going to give you 21. So you'd have found your f of x0. This bit is 21. Similarly, you work out what is the value of the derivative at x0. So in that case, f prime of x0, that's going to be f prime. You put a 2 there. So in this case, this is your expression for the derivative. So that's going to be 5 times 2 to the power 4 minus 4 times 2. And you're going to get yourself 72. Are we clear? Is it clear? Hello?
Yes, it is.
Okay.
Yes, it is.
Next, these values you have found for f of x0 and for f prime of x0, which are what you have here and what you have there, you substitute them there. So you're going to end up having x1 is equals to, instead of x0, you put x0, that's going to be 2 minus 21 divided by 72. 21 divided by 72, you're going to get something, then you subtract it from 2, you end up with x1 equals to 1.708333. So that is your value of x1. Are we clear?
Yes, sir.
Next, we work out what is the value of, next we work out the second iteration. We go for k equals to 2, for k equals to 1. Remember we did k equals to 0. Next we work out k equals to 1. For k equals to 1, our Newton-Raphson method becomes x2 is equals to x1 minus f of x1 divided by the derivative of f at x1. Is that clear? So again, in this case, we need to work out what is the value of the function at x1 and what is the value of the derivative at x1. So x1 we have just found. X1 is what you found here. This is our x1. We've just found out to be here. This is x1. Then we work out so f of x1, that's going to be f of 1.108333. So that's going to be 1.708 333 to the power 5 minus 2, 1.708 333 to the power 2 minus 3, and you're going to get yourself a 5.71319717. So this is going to be the value of the function at x1. Similarly, you work out the value of the derivative at x1. So that's going to be f prime of 1.708 333. So you're going to have 5 times 1.708 333 to the power 4 minus 4 times this much, 1.708 333. That's going to give you 34.8 0.043770717. So the value of the function at x1 is this, the value of the derivative at x1 is this. So we have things to substitute. So we can, this bit here, what you have here, that's what you're going to substitute here. This lot which you have here, the value of the derivative, that's what we're going to put here. And we also know what x1 is. x1 is just this value here, this bit here. That's x1. That's what you're going to put there, so that we can work out x2. So in that case, when you do that, you end up having 1.708333 minus the value of the function at x1 divided by the value of the derivative at x1. So when you divide this divided by that, so whatever you're going to get, then you subtract it from this number here, you get your x2 as 1.540513.855. So this becomes your new value of x2. This is just after the second iteration. After the second iteration, as you can see, we are already at 1.5. If you look at the function which we have, if you look at the curve for the function, you can see that the root is somewhere at 1.5. So with the Newton-Raphson method, already, only after 2 steps, we are already at 1.5. If you look carefully, here, you can see somewhere there, the root is at 1.5, somewhere close to 1.5. And so with this thing which are doing, with our choice of guess value, you can see already we are getting to where we suspect the answer is supposed to be. Is it clear?
Yes, yes.
Okay. Next, we work out for k equals to 2. So we've done k equals to 0, k equals to 1. Next, k equals to 2. For k equals to 2, the Newton-Raphson method becomes this. x3 is equals to x2 minus the value of the function at x2, then the value of the derivative at x2. So we have x2. x2 is 1.540513.855. So we work out what is the value of the function at x2 and what is the value of the derivative at x2. So the value of the function at x2, f of x2, that's going to be f of 1.540513.855. So you put in your x2 value here, that's your 1.54513.588 squared minus 2, then 1.540.513.855 to the power 2 minus 3, and you're going to get yourself a value of this function at x2 as 0.929803297. Next, you work out what is the value of the derivative at x2. So that's going to be f prime of 1.540.513.855. So that's going to be 1.540.513.855 to the power 2 minus 4, 1.540.513.855, and you're going to get yourself 21.99793.085. So you have the value of your function at x2, which is this. You have got your value of your value of your derivative at x2, which is that, and you have your x2 itself, your x2, which is this. So we can make substitutions here so that we can find what is our estimate of x3. So in this case, x3 is going to be equals to 1.540.513.855. This is our x2. Then the value of the function at x2, this is what you have here, from here. Then the value of the derivative at x2, this is what you have here, from there, like that. So you work out, you start with this, you do the division, then after you divide, then you subtract from here. When you do that, you end up with x3 is equals to 1.498246065. as your x3. Are we clear?
Yes, sir.
Next, you can work it out. So we want to see how the whole thing goes. You work it out for k equals to 3. Now for k equals to 3, your Newton-Raphson method iteration formula becomes x4 is equals to x3 minus the value of the function at x3 divided by the value of the derivative at x3. What we have found out so far is that our x3 is this one. Then we need to find out what the value of the function is at x3 and what the value of the derivative is at x3. In this case, your value of the function f of x3 is going to be f of 1.498246.065. Then you end up having this 1.498246.065 squared to the power 5 minus 2 1.498246.065 to the power 2 minus 3, and we end up having this as the value of the function at x3. Then you also work out what the value of the function is at what the value of the derivative is at x3. So in this case, you're going to end up with the derivative at 1.498246.065. That's going to be 5 to the power 5 times 1.498246.065 to the power 4 minus 4 1.498246.065, and you end up with 19.20133268. So we have the value of the function. We know x3. We have the value at x3 of the function at x3, which is that. We also have got the value of the derivative at x3, which is what you have here. So when we substitute for x4, we end up having x3, which is what we have here, 1.498246.065. Then you put in the value of the function there. Then you put in the value of the function at the derivative at x3, like that. So you work out this division divided by that. Then you subtract from this. Then you end up with x4 equals to 1.495126. So what you start seeing something here, that the value of x stops changing too much. Already for x3, the first 3 digits have stopped changing. Our x3 is 1.498246.065. Then these first 3 digits have stopped changing. For x3 and x4, you see that the first 3 digits have stopped changing, like that. So basically, now your tangents are closer and closer to whatever it is you have. And also, the other thing to use is you have to look at what is when you get your solution, this solution here. You've seen x3. What is the value of the function? Because if x3 is the answer, then this function at this value of x3 must be equals to 0. Already you can see x3 is already a good solution. It's equals to 0.05 something. Is that clear? Is it clear?
Yes, it is.
Already you can see that x3 is actually an acceptable solution at 1.498 whatever it is. The other one, x2 is not, it's okay, but it's not a good solution. x2 is equals to, the value of the function at x2 is 0.929. It's not very close to 0. Okay, so if we look at what we have with x4, what have we found out with x4? So with the x4, in our case, so you end up having, we can work out for x4, this is what you found. Okay, then there's something I think which some kind of a rewrite I think I was supposed to do immediately after evaluating x4, whatever it is. I should have been working out the value of the function like this. So this is the value of the function at x4. So you can see how x4 is. If you put in x4, what you get 3 times 10 to the power 7 here, 3.0709782 times 10 to the power minus 4, which is very, very small. So x4 is already a very good solution. Are we clear?
Yes, sir.
Yeah, x4 is
Yes.
this x4 which you have here is already a very good solution, because remember, what we are doing with these methods is not that we are trying to find exactly f of x equals to 0. What we are trying to find is f of x approximately equals to 0. Okay. So the other thing which I do next, I think, is just trying to show you that once you work out, you see what the value of the function is. So immediately after you work out an answer like this, you're supposed to work out what value does this particular function have, so that you can see if the answer you have found is acceptable enough or not. Okay, so if I proceed like I did, I proceeded to work out for k equals to 4, there would not be much difference, as you are going to see, in what I have. Between x equals to 4 and x equals to 5, there would not be any appreciable difference. So let's see. So for k equals to 4, so I'm going to end up with a Newton-Raphson method, which is equals to x5 equals to x5 equals to x4, then the value of the function at x4, then the value of the derivative at x4. So I work out what the value of the function at x4 and what the value of the derivative at x4. So in this case, the value of the function at x4, which is equals to f of 1.495126, that would be 1.4951226 to the power 5 minus 2, 1.495 to 1.4951226 to the power 2 minus 3. This is what I get. I get a very, very small value of the function at that particular thing. So that's showing me that x4 is already a very good solution. Okay, then I proceed to work out the value of the derivative at x4. So in this case, the value of the derivative at x4, that's going to be equals to f of 1.4951226, that's going to be 5, then multiplied by 1.4951226 to the power 4, then minus 1.49 times 1.49512 to the power 6, and I get this. So I will be dividing. Now this is the value of the function at x4, this is the value of the derivative at x4. So I put in for x5, so I put in x4 minus the value of the function at x4 divided by the value of the derivative at this bit. So when I do this division and this division, I'm dividing a very small number divided by a significantly larger number. So basically I end up with almost 0. When I end up with almost 0, then whatever it is I end up with here, I subtract from here. When I do that, I end up with x5, which is equal to 1.495106398. So I end up with this 1.495. What do I have on top here? I have x4 equals to 1.495. Actually, it even goes further up to here. x4 equals to 1.4951. The first 1, 2, 3, 4, 5 digits remain unchanged. As you can see, between x1 and x5, the first 5 digits remain unchanged. The only thing which changes now is the 2, which becomes 0 here. So when you work out what this is, the value of the function at x5, the value of the function at x5, which is f of 1.495106398, so that's going to be this. Then you work out what this is, you end up with something which is very, very small, 8.2482 times 10 to the power minus 9. Much, much, much smaller. So in this case, as far as I'm concerned, you could pick your x5 as a solution, which is what I've done here, 1.495.106.398. Well, basically, you can just pick a solution up to this point here, up to 4 decimal places, 1.49515. So 1.49551 up to 4 decimal places as your solution to that bit. But you can pick that one. You can also pick this one. This also is an acceptable solution in this case. Are we clear?
Yes, sir.
Any questions?
I have a question, sir.
Yes.
Through program or
What?
like these questions that we do, like the work list out. Do we work it out? No questions come just like that. We need to induce it in programming, like we make the computers work this out.
We'll show you how to make the computer work this out. But for your test, your actual test, because one, remember, you're going to have your labs, then you're going to have a lab test, then you're going to have assignments. For your assignments, you work it out on with pen and paper. For your tests, so you work these things out with pen and paper. For your exam, you work these things out with pen and paper. It's only for your labs and for your lab tests where you have to use a computer to work these things out. Are we clear? Yeah. And that is exactly the reason why, since you people are at home, I have come to the conclusion that in order to push you, because I've got no way of making sure that you be studying or you're doing things. That is the reason why at the end of each chapter, you are going to get an assignment. An assignment which contains 2 questions or 3 questions, depending on whatever it is we have. Like in this case, we're going to look at 3 methods. So I'll give you, on each method, I give you a problem. On each method, I give you a problem. You work out those assignments, then you submit them, then I mark them, then I see how you're doing. If people are understanding or not, because I don't want a situation where people think they know something only to find out in a test that people don't know. The other thing is, if you are going to decide to copy from your friends, you datuka, then you submit, you're just cheating it yourself. Because those assignments are only going to be 5%. Your assignments are only going to be 5%. Then you've got the labs and the lab tests, which are 25%. Then you've got your tests, which are 20%. Then you've got the exam, which is 50%. So if you decide to say you are not going to actually do the work yourself, you're going to be copying from your friends, you are going to fail. Because even if we give you the formulas, these Newton-Raphson method formulas, the bisection things, we are going to give you the formulas, but you would not know what you are supposed to do. You won't know what you're supposed to do because you did not practice. Are we clear?
Yes, sir, we're good.
Yeah. Now, the other thing I want to do is we have to go a bit beyond time. I want to finish example number 4 so that when we meet tomorrow, I don't know whether, what I don't know how we're going to do it. What's coming after this?
This is the last lecture today.
Okay. So remember we changed something. We changed the time for the Friday class. We had promised ourselves that the Friday class would be starting at at 12. Now the Friday class is starting at 13. Then it ends at 14. So I think that 1 hour which we need, we're going to put it on top of this one, so that we have our class on Thursday from what time did we start? From 15? Yeah, we have our 2 hours from 15:17. I need to finish this example so that tomorrow we can start on a new page. I need to get rid of this chapter this week, so I can give you your assignments, I can give you your tutorial sheets. Your tutorial stuff is for you to work out on your own. You can consult with your friends, see what the answer is, whatever it is, but you're not going to submit your tutorial questions. The only things they're going to submit are assignment questions. The assignment also is going to be put on Moodle, so you are going to submit through Moodle. Then whenever I have the time, I'll mark these things. Are we clear?
Yes.
So as much as you can attend the class, you have to make sure that since you're submitting through Moodle, you have to make sure that your registration is up to date. If you are not registered, you will not be able to submit your assignments. Are we clear? I'm doing my part. I don't know if you are registered or not, but you have to make sure that you're registered so that you're able to submit your assignments. Also, most likely, you're going to write your tests from home. So if you're going to write your test from home, that test will have to be submitted through Moodle. If things continue the way they're going, most likely you guys, I don't know if you're going to come back to campus or not. So for now, things will have to happen through Moodle. So make sure your registration is up to date. Make sure you can access Moodle without any problems. If you have paid the university and you're still having trouble with Moodle, make sure you call someone and they fix your stuff. Otherwise, the only bit I have to do is I just have to teach. Okay, so we proceed with example number 4. As you can see, example number 4 is a quadratic equation. Find the root of the equation f of x equals to x to the power 2 minus 2x minus 1 equals to 0. This is a quadratic. Now, the other thing we have said is that these methods are looking at bisection, Newton, Raphson method, and other things. You can use these methods also even in a case where it's possible for you to work out something by pen and paper. You can always work out a quadratic with pen and paper, but a computer is always going to be faster. Right now, because we are doing it by hand, trying to see how the algorithm works by hand, it looks like it's tedious. But the moment you write a program which works out, which follows this procedure and works out Newton-Raphson method, you get your answers in seconds. Are we clear? Is that clear?
Yes, sir.
Yes. So we do not only use these methods for equations where you can't find the answer directly. Sometimes you don't have time to do things with pen and paper. Then you put up something, then computer works it out. So in this case, we have got this bit, x squared minus 2x plus 1 equals to 0. And how does this function? And we're starting with a guess value x0, which is equal to 3.5. And how does this look like? This is our function between 1 and 4. So this is what it looks like. Between 1 and 4, it looks like that. Your x squared is equal to minus 2x plus 1. So between 1 and 4, it looks like that. And you can see it cuts the x-axis somewhere there. Between 0 and 2.5, but somewhere more close to 2.5, somewhere there. So what we are starting with a guess value, which is here, 3.5. Our x0 is 3.5. Now, this function, as you can see, it's suitable. It's very suitable for Newton-Raphson method because our function f of x is very easily differentiable. Are we clear? You should use Newton-Raphson method with a function that you can easily differentiate. Is that clear? So, since we can easily differentiate our function f of x, then we're going to work out what the derivative is. So the derivative of f of x is going to be this is the function x squared minus 2x x squared minus 2x minus 1. This this bit is not there, so we end up with 2x minus 2. So this is our derivative. So for k equals to 0, there, so for k equals to 0, our Raphson method, Newton-Raphson method becomes x1 is equals to x0 minus f of x0 divided by the derivative of the function f at x0. We know what x0 is. X0 is 3.5, so we can work out what the value of the function is at x0 3.5, and you can also work out what the value of the derivative is at x0 equals 3.5. So in this case, f of x0, that's going to be f of 3.5, that's going to be 3.5 squared minus 2 times 3.5 minus 1, and you're going to get yourself 4.25. Then the value of the derivative at x0, that's going to be f prime of 3.5, that's going to be 2 times 3.5 minus 1, you're going to end up with 5. So we have the value of the function at x0, we have got the value of the derivative at x0. So we can put these values here, there we put 4.25, here we put the value of the derivative 5, then here we put our x0, which is 3.5. When you do that, so we end up having x1 equals to 3.5 minus 4.25 divided by 5. You do this thing first, 4.25 divided by 5, whatever it is, then you subtract it from 3.5, you're going to end up with x1 equals to 2.65. Is that clear?
Yes, sir.
Next, as you're going to see, your x1 equals to 2.65 is not yet a good solution. So we have to do this again. So after this stage here, my advice, I think I need to probably make a, I don't know whether I should do, no, maybe for next year, do another revision of this node so that I can work out the expression here. But as you're going to see, for x1, the function does not have a value which is close to 0. So in this case, we move for k equals to 1. So in k equals to 1, our Raphson method becomes x2 equals to x1, then the value of the function at x1, then the value of the derivative at x1. So in that case, our x1, which is 2.65, so we work out the function. The value of the function at x1, that's going to be f of 2.65, that's going to be 2.65 squared minus 2 times 2.65 minus 1. You end up with this. You end up with 0.7223. So you can see that this solution which we have, x1, yeah, but it's not very close. It's 0 point something, but it's not very, very close to 0 with the stuff we can achieve. So x1 is not a good solution. So we need to do another step. Then work out the value of the function, the derivative at x1, that's going to be f prime of 2.65. That's going to be 2 times 2.65 minus 2. You get yourself a 3.3. So with the value of the function at x1 known to be 0.7223, and also the value of the derivative at x1 3.3, we substitute, we make our substitutions. For x1, we put in our 2.65, then the value of the function at the x1, then the value of the derivative at x1, we put in what you have found. So this is the value of the function at x1, this is the value of the derivative at x1, so we put in there, so we end up with x2 is equals to 2.65 minus this bit divided by that bit. So we work out this thing first. When you do that, you end up with 2.24311212114. This already, as you can see from the graph, we have 2.4. As you can see already from the graph, it's already a good solution because the graph cuts somewhere there. This is 2.5. So what we have is 2.4. So already just after the second iteration, we have an answer which seems acceptable. Just after the second iteration, we have an answer which seems acceptable. And how do we know that it's acceptable? If you look here where we are evaluating f of x2, this is our x2. F of x2 is equals to f of 2.43112122. That is equals to 2.431 121 212 to the power 2 minus 2, this 2.431 121 213 minus 1, this is equals to 0.04814793. So you can see it's already 0.0 something. That's why we're saying already we have something which is acceptable. Is that clear?
Yes.
Yeah. So we have our x2, which is okay, it's a good solution, but we can do better. So we move on to another iteration. We work out for k equals to 2. So now for k equals to 2, that means that we have to, our Raphson method becomes x3 equals to x2 minus f of x2 divided by the derivative of the function at x2. So this is our value of the function at x2. So that's what we have here. We have 0.048107 Then we work out the value of the function at the derivative. In this case, f prime of 2, that's going to be f prime of 2.431 that's going to be 2 times 2.431 121 minus 2. You end up with 2.863 424 this. So this is the value of the function at the derivative, and this is the value of the function at, sorry, this is the value of the function at x2, and this is the value of the derivative at x2. So we substitute for the value of the function, which is this, we put this guy there. For the value of the derivative, which is this, we put this guy here. Then of course there is the x2 itself, which we already have, which is this, which you found out earlier. You put it there. When you do that, you end up with x3 equals to 2.431 121 212 minus whatever the value of the function is divided by the value of the derivative at x2. You end up with x3 equals to 2.414313438. That's your x3. If you work out the value of the function at x3, as you can see from here, that's at x3, you get a very good value. You can see that the value of the function at x3 is very, very small. You end up having 2.80385969 times 10 to the power minus 4, which is a very good value. Are we clear?
Yes.
Yeah, so x3 is actually an acceptable solution in this case. But of course, if you want to stretch things, you can go further to see if you can get something better, and it's not going to be much better, but it's going to be more kind of accurate, but not so much accurate compared to what you have for x3. So you're not going to gain very much, basically. So for k equals to 3, you're going to have a Newton-Raphson method becoming x4 equals to x3 minus the value of the function at x3 divided by the value of the derivative at x3. So in this case, your x3, f of x3, that's going to be f of 2.412313,483. So you're going to have 2.414313,483 squared minus 2 times 2.414313,483 minus 1. You end up with this, 2.80385469 times 10 to the power minus 4. Then next, the value of the derivative at this particular, sorry? Is there a question?
No, I'm good, sir. I was just following through.
Okay, so the value of the derivative at x3, so that's going to be f of 2.414313,483. So that's going to be 2 times 2.414,313,483 minus 2. So you end up having 2.828626,873. This. So we've got the value of the function at x3. We have got the value of the derivative at x3, like that. So with this bit, we substitute. So you end up having, so you, for x4, you're going to have 2.414313,483 minus this bit, the value of the function at the at x3 then the value of the derivative at that bit. So whatever it is here, you work it out, then you subtract from this bit, you're going to end up with 2.414214313. Then if you work out the value of the function at this particular value here, you do your stuff. 2.414214314 squared minus 2.414214314 minus that, you end up with this. You end up with x4 being equals to f of the value of the function x4 being equals to 2.12592249 times 10 to the power minus 6, which is very, very small. So either x3 or x4 is acceptable. Are we clear?
Yes.
Yeah, so basically that's where we're going to end today, hopefully. What comes next is something called the second method. We're going to look at that tomorrow, but the thing I'm going to do is, since you guys were not prepared for the extended class, I'm going to modify my Google Calendar so that it can reflect this extension we're going to have on Thursdays, so that we can meet from, actually I think we can meet from it's not exactly going to be 2 hours, because I've got another class with first years at 17 hours. So basically we can have from 15 to 16:30. Okay.
Yes.
So if there's something to be done, then it can be done at that particular time, and that's what you have done. So we have covered 2 examples. So tomorrow when we meet, we are going to look at a method called the second method. Yeah.
So I have a question. Like this, which you're from doing, is it any different from these other functions under mathematics? Like
What?
the principles, I'm noticing it's in a way similar,
This is mathematics.
but just a normal.
This is what's referred to as numerical mathematics.
Okay.
Yes.
Okay. Then we're good. We're very good.
Yeah, this is mathematics, and that's how basically we're trying to do the steps which our computers are going to go through as they are trying to find answers for us.
Yes.
Yeah.
Okay.
All right.
So thank you.
Okay, so see you tomorrow at 13 hours.
All right. So cheers. Take care.
Good.